Okay, let's get started here. So project number 1 is due on Thursday. I expect that we will be able to get through the rest of the material in Chapter 2 today that corresponds to the project. If for some reason we are unable to, then the project due date will be moved. We will continue then in Chapter 2, Part 1 notes. I doubt that we'll get to the Chapter 2, Part 2 notes. So, are there any questions before we get going here? Yes?
I guess maybe I'll ask a question. So when you're doing the parametric bootstrap using the boot function, you have to put in the MLE as one of the parameters.
Yep.
That doesn't necessarily have to be the MLE.
Yeah, that's just the name of the argument,
Okay.
which happens to often be the MLE.
But doesn't need to.
But it's not implying to put this MLE there.
Not necessarily.
Okay.
Other questions? Okay.
Real quick, you said on the project to take out the plus signs. What about the arrows? Like the greater than arrows before it. When you copy the code from R.
You mean like X gets?
No. At the input stage.
Oh, leave the arrows in because
Okay.
it tells me what where
input.
each command is.
Okay.
Is it okay if we took the arrows out? Should we put them back in?
If you're already taking them out, leave them out. But in the future, please leave them. Any other questions? Okay.
Details. You want me to be right.
No, that's fine. Okay, so we were talking about confidence intervals. Just started talking about confidence intervals last time. 1 minus 2 times alpha times 100% confidence interval for theta is found from examining this corresponding probability. The probability of the lower bound is less than theta is less than the upper bound. It's equal to 1 minus 2 times alpha. So the actual, these L and U are statistics. So they're based upon the sampling distribution for T minus theta. And let me get a red pen here. And the actual interval in the end that you would calculate is, you replace the random variable version of the statistics with their observed values. So if this is, let's say, a lowercase l, L is less than theta, it's less than a lowercase u, of course. And that is the actual interval itself. So that takes us then to talk about 2 different kinds of Bootstrap confidence intervals. Chapter 5 is a whole chapter on Bootstrap confidence intervals. And we'll learn about other confidence intervals out there. Please note that the first one that we're going to talk about is not necessarily the best interval to use. And the reason why we talk about it is because it's an easy interval and it helps motivate other intervals that we see in Chapter 5. The second interval that we talk about is one of the 2 leading Bootstrap confidence intervals out there. So we're going to talk about the basic Bootstrap confidence interval. Now you will often, well, sometimes hear this also called a hybrid Bootstrap confidence interval too. And it's a very intuitive derivation for it. First of all, let's not think about the Bootstrap itself. And let's say that I have T minus theta has a corresponding CDF of G of T given F. It's going to be important to make sure that we have the F there so we know what we're talking about. And a corresponding quantile from this distribution, of course, is G inverse of 1 minus alpha given F. Okay. Now, what I want to do is find a confidence interval for theta. Here's how we can derive it in this context. So we know the distribution for T minus theta. So that allows us, and we'll call this step 1 of, if you want to call this a proof, it's not really a proof, but we'll just say step 1. And so the probability that t minus theta is in between two quantities can be easily found from using these quantiles from the corresponding distribution itself. So the alpha quantity, the alpha quantile and the 1 minus the alpha quantile. Now our goal is going to be just to get theta itself by in the middle of this inequality. So let's subtract t. This is step 2. So let's subtract t from both sides, or from all three parts, you can see inside there. And then we want to get rid of the minus in front of the theta, so we multiply through by a minus, and that changes the signs. But also, of course, it changes the direction of the inequality. And then lastly, step 4 here, we just put stuff in the correct order that we would expect, so that the lower bound is on the left-hand side, and then the upper bound is on the right-hand side. Okay? So from that, then, we can say what our confidence interval is. Replace the random variable version of the statistic with this observed value, and there's our confidence interval. So notice all you do is you take t minus then 1 quantile, that's the lower bound, and the upper bound is t minus a different quantile. But be careful with respect to which quantiles we're talking about. This is not a typo here. Notice how I have, you could say, the upper quantile from the distribution on the lower bound. Also, I have the lower quantile of the distribution on the upper bound. Does that look odd at all? Good. I'm glad some people said no. Because all of you should have seen this before when you've talked about a derivation for a confidence interval for, let's say, mu, using just a regular old t-based interval. Just to review, the way that you would go about actually deriving it is that you would have started off with something like this inside of a probability argument. So notice how I have the lower quantile from a t-distribution, and I have the upper quantile from a t-distribution. And through the algebraic steps that you go through to only have mu in the middle of this inequality, what ends up happening then is that you get the upper quantile on the left side and the lower quantile on the right side. Now, does that interval look a little bit different from how it's usually presented? Yeah, because normally you have plus t 1 minus alpha n minus 1 degrees of freedom on the right-hand side there. Well, of course, we know the t-distribution is symmetric, and so that's why whenever it's actually presented to students in a classroom, that's why you have the plus version of this there. And that way you have exactly the same quantile. But in a very generic setting, this is what the interval looks like. Any questions? It's important that you understand this concept. Any questions? Okay. So, now, let me go back up. So, if I knew the distribution of G, great, I could get the interval. Problem is we don't know the distribution for G. So what do? Well, put a little hat on top of the F in there, and then that will allow us to estimate the distribution of G. That will lead then to the the basic Bootstrap Confidence interval. So, indeed, here it is. Well, what is this G inverse of 1 minus alpha given F hat? Well, we talked about this actually earlier when we were looking at estimating quantiles from a distribution. So, all that this notation means is I want now the the 1 minus alpha quantile from the distribution of T star minus T. Of course, it's going to be very unlikely that you're going to be able to figure out this exactly if you're in the non-parametric bootstrap setting. In case I didn't say so, we are right now. F has the EDF. So how do we estimate this? Well, we take a bunch of resamples and find the R plus 1 times 1 minus alpha order T star, subtract that from T. That will give us the 1 minus alpha quantile, and then and do a similar thing for the alpha quantile.
So just to clarify in my own mind, so here theta and little t are the same thing.
No. You know, T minus theta has a distribution of G. T star minus T has a distribution of G hat. And we're using T star minus T, that distribution, to allow us to get the quantiles, to estimate the quantiles. Also, make sure you understand with this notation here, this G is represented like this in my notes. And this G hat is just represented like that in the notes due to the equivalence of the different notation. So, you know, maybe it's helpful too to think of it in terms of a confidence interval for mu. You know, in that case, we know our distribution. You know, it's the T distribution. Sorry to have another T out there. But it's the T distribution. Well, that relies on the Y's having a normal distribution, of course, to get it. That's why we were able to get at what G was. But, you know, in actual application, are you ever going to really know what the Y's are? No. So what this does here basically follows the same steps that you would with the usual confidence interval for mu, except for now we generalize it to any parameter of interest, call it theta, and for any distribution for the statistic of interest. So then the actual interval that we would calculate, a non-parametric interval, would be this. T minus the estimate of that 1 minus alpha quantile is the lower bound. The upper bound is T minus an estimate of the upper quantile. I'm sorry, I said that wrong. T minus 1 minus alpha quantile, the estimate of that. I can't talk today. Let me restate that one more time. Or should I say, here it is. Any questions? Notice there's a nice little simplification because we have a minus T there. I want to just bring it over, and so that we have actually 2T minus that quantile. That's the lower bound. The upper bound is 2T minus this particular quantile. And that is the non-parametric basic bootstrap confidence interval. Okay, so here's a question then. How would you obtain this 1 minus alpha quantile if a parametric bootstrap was used? First of all, let's consider from the case of without actually taking resamples. So let's go back here. If I wasn't actually taking resamples, how could I get this quantity? Well, you get, let's say that you get the estimates so that you get an F hat that's a parametric, like maybe on normal. And then from that, depending upon the form of T minus theta, you could derive the actual distribution for G. So, you know, think of it from a simple perspective of a confidence interval for mu and the Y's originally were normal distribution. Well, what would be the distribution of G here? Well, what's the distribution of the sample mean minus the population mean? Well, it's normal. It means 0 variance of sigma squared divided by n. So put a hat on top of the sigma squared, and there's your t minus theta distribution of this. Okay. Now, what would you have to do if you actually wanted to take resamples? Get f hat. Perhaps this is
Just do the same process that you did if you have non-parametric.
do the same processes with non-parametric. All you do is change how you get the resamples. So you sample from the f hat distribution. That would be like a normal, let's say, x bar s squared divided by n. Now notice here that we are actually working with some extreme quantiles because alpha is going to be small, like 0.025 for a 95% confidence interval. So we need to be careful with the number of resamples that we take so we get good estimates of the edges of this distribution. So the book says at least 1,000. I guess whenever I do these in practice, I usually use at least 1,999, even 4,999 resamples as well. So just realize that it's hard to estimate then these extreme portions of the distribution, and so because of that you need to take a large number of resamples. The extreme case is, let's say that you want a 99% confidence interval and you only took r equal 100. Think about what would happen in that particular case, what t stars you would take. Or r equal 99, maybe I should say. And think about, do you think that would be a good estimate or not? And we kind of talked about that before as well. So how good are these intervals? How do we measure accuracy with respect to a confidence interval? Width would be one way to evaluate the interval. I guess I'm thinking about accuracy in terms of coverage. Sorry, I guess I gave away the answer. In terms of the true confidence level. So we might state 95% confidence, but in actuality, it's probably not going to be exactly 95%. Maybe it's 90%. Maybe it's 99%. Maybe it's 50%. So we're very interested in accuracy, and in Chapter 5, we'll actually do some simulations to examine how good these intervals are. But for right now, let's talk about some general concepts of how to get your accuracy, the coverage level of this interval to be good. And you're going to see a common theme throughout this course in terms of when we're dealing with the Bootstrap, and that is we want, obviously, the distribution of t minus theta to be very similar to t star minus t. The closer they are, of course, the more accurate your Bootstrap estimates are going to be. How can you get them to be close to one another or be similar? Well, hopefully all of you remember in a Stat 883 class the concept of pivotal statistic. Pivotal statistics do not depend upon, the distribution does not depend upon any unknowns. If you can get a t minus theta to not depend upon any unknowns, that t star minus t is likely not to depend on any unknowns, and thus the distribution are going to be more likely to agree. Let's think of it from an intuitive standpoint. Let's say that t minus theta, that distribution actually depended upon another parameter. So that means then, of course, then t star minus t is also going to depend upon likely another parameter. And so where do you lose accuracy? Well, the fact that you're going to have to estimate that parameter for t minus theta and also for t star minus t. It's just an intuitive idea behind that. So we often want to work with pivotal statistics when we're dealing with the Bootstrap. So one of the very first pivotal statistics that you probably ever learned about was the old pivotal statistics that you used when you constructed a confidence interval for the population mean involving the t distribution. So, especially if we're in a non-parametric setting though, what's a pivotal statistic? How do you define a pivotal statistic? Because you don't have a parametric setting. How do you define unknown parameters? So that leads us then into what's called a studentized bootstrap confidence interval. Sometimes it's called a bootstrap T. And notice the names there. T, bootstrap T, studentized. So you might think it has something to do with how we form that little statistic there. And in fact, it does. First of all, this interval was developed by Peter Hall in the 1980s. Hall is probably one of the most prolific researchers out there. If you pick up an issue of Jazz, you're likely to find a paper by him in there. He's based at University of Melbourne, and also, I think he also has a joint appointment out like Cal Davis here in the U.S. And when people say the bootstrap, you say the word the bootstrap in a statistical sense, people typically think of Bradley Efron. But probably the second person that people think of, at least I do, when someone says the bootstrap, I think of Peter Hall for the work that he's done in it. So anyway, so studentized bootstrap confidence interval. So why don't we kind of mimic this idea of finding a studentized statistic? So instead of just working with t minus theta, how about we work with t minus theta divided by an estimate of its, the square root of an estimate of its variance. So again, with our notation here, just to make sure it's clear, this V also is basically this, an estimate var hat of t. And I could put an F in there as well if I wanted to give an F. So V, and then notice it's a capital V, so it's the random variable version of an estimate of this variance for a statistic of interest. And we're going to call this Z for kind of, the usual reasons. We often call a quantity like this, where you take the quantity divided by its variance, a Z value. But take a look at this in terms of a statistical function. So this T can be written as T of F hat because it's a function of your sample, and theta is T of F. But now we introduce this little slightly different notation, V of F hat, to emphasize that this estimate is also based upon your data, your sample, your original sample. Now, in this kind of a setting then, what you could do, if you knew the distribution of Z, you could find, let's say, the alpha quantile from the distribution of Z. The way I'm going to denote this is as Z with a subscript alpha is less than Z, is less than Z 1 minus alpha quantile. That's equal to 1 minus 2 alpha. Those are Z's, even though they don't look very good like Z's. Those are Z's. So then what I could do is simply plug in what Z is into this probability statement, do some algebra, so that I just have theta in the middle, and then take the observed values of the random variables, and here is my confidence interval for theta. I'm not doing the bootstrap yet. Not really doing the bootstrap yet. That will be my confidence interval for theta. And again, this is just how a confidence interval for mu using a t-distribution is actually found. Except for now I just have different symbols in there instead. Instead of having x bar, I have t. Please note that small change here to the notes. So that's parentheses around the t minus theta, divide by v to the 1/2 power. Now, just because I'm using this Z there, I'm using quantiles from some kind of distribution of Z. This is not necessarily a normal distribution. Okay, it's just I have some random variable, and the way I'm denoting its quantiles from its distribution is with a little subscript to that random variable. That's all. So, from this, what can we calculate from our data? Our original sample. We can calculate T, we can calculate V as long as we have a formula for it. That's going to be an important thing coming up. But what do we use for this quantile from this distribution of C? That's where the bootstrap comes in. Well, we just simply use the bootstrap to estimate the quantile from that distribution. That's all. So, well, what's the bootstrap version of Z itself? Well, we call it Z Star. Well, now we have T star minus T over V star raised to the 1/2 power. So what this means is, again, take your resample, calculate the statistic of interest on the resample, subtract off the observed value of the statistic in the original sample, and then calculate this estimate of the variance. If you have its formula, calculate this estimate of the variance on the resample data itself. That's your Z star. In the context of statistical functions then, of course, our original T will be T of F hat. Well, look at this other little notation I'm using here. T star is represented as T of F hat star. What does that mean? Well, F hat is the EDF for Y1 through Yn. Then F hat star in our book's notation is the EDF for Y1 star down to Yn star. So it's just the EDF of a resample. So what this notation emphasizes is the fact that you've had to calculate this quantity on the resample data. Just to foreshadow some stuff that we're going to be doing later in Chapter 2. What do you think that notation means? It's supposed to be an F there, not a... It's supposed to be an F. EDF for Y1 star star down to Yn star star, which is a resample from your resample. This is called the double bootstrap. And you can keep on going adding stars there if you wanted to. You'll see where this comes in handy later on to take a resample for your resample. But you can also think about, geez, if I'm already taking capital R resamples already, and if I have to take a resample from each of those resamples, let's say each of the resamples from the resamples is the size of M, well, look at how many resamples you're taking. Like approximately R times M. That's a lot. So, this is where stuff can get long, or take some time when you're doing the bootstrap. Okay. So, if I can then calculate this quantity for each resample then, that's going to allow me to estimate the distribution of, that will give me the distribution for Z star. And then that allows me then to get an estimate for the distribution for Z itself. So how about we replace the original quantiles that we had in our previous confidence interval formula now with these quantiles for the distribution of Z star. And again, I take R plus 1 times 1 minus alpha ordered Z star value, and R plus 1 times alpha ordered Z star value. And that is the studentized bootstrap confidence interval calculated in a non-parametric sense. Often this kind of interval is explained using the following analogy, and that is, when we calculate a confidence interval, for mu, if I just write out the old formula, the thing that we have, I cannot write today. The thing that we have to do here is, or at least that we used to do long ago before there was R and other simple software packages, we have to actually go to a t-distribution table and actually look that value up. Does anyone actually do that anymore? I hope not. Anyway, just plug in the right formula in Excel, plug in the right formula in R. It's a lot simpler than having to teach students how to use t-distribution tables, normal distribution tables, all those different kinds of tables. But anyway, so you would go to a t table. So essentially what we're doing here is, by doing this little simulation, is that we're coming up with our own version of a t-distribution table, or our own distribution of the table. That's comes about through the Bootstrap. What happens if we were doing a parametric Bootstrap here? What would we do if we had to actually take resamples? How would we get this guy? We figure out what f hat is. It's going to be some kind of parametric distribution. We take our resamples from that. Every resample, we're going to need to know what, obviously you'll know what t star is, but you're going to also need to know what the variance of that is too. Calculate this for every single resample, find the corresponding quantile. Let's say that you didn't want to use resamples. What would you need? You need the distribution of Z star. You would need to actually derive this. It may or may not be easy, depending upon what T star and V star are. Okay. Now, this is on page 60. Now, one thing that we haven't really discussed is, well, what is V? What should we use for V or V star? Again, remember what V is. It's the estimated variance of your statistic of interest. Well, if I had a simple statistic such as maybe Y bar, well, we know that that variance is sigma squared divided by n. So if I want to come up with an estimate of it, I just put little hats on top of it. We know how to estimate sigma squared. Use the sample variance, for example. Well, let's say instead that my statistic of interest is this. What is that statistic? Hopefully I wrote it clear enough. It's S divided by Y bar. Coefficient of variation. Does anyone know what the variance is for the coefficient of variation? No? Someone to derive it right now? Come on. Extra credit. I don't know what it is. Well, let's say you want to do this in a completely non-parametric setting. What would you put in for V star? That's what you will need V star in order to do this. So, what can we do? Well, perhaps what you could do is this. Suppose you had the asymptotic variance for t. The asymptotic variance for coefficient variation is not too difficult to derive if you've had Stat 980. And you could use that. And even though it's an asymptotic variance, it at least gives you some measure of variance. And you could use, you have a formula for it, get the estimated asymptotic variance, and then use that, for V, and then for V star, just calculate the same formula on the resamples. Every single resample, of course, will have a different V star, as long as the resamples are different. That's a very, very key point to understand. Every resample is going to have a different V star. sorry, I'm kind of jumping around here in my explanation. The reason why I mention this is because it's very, very easy to think that you calculate maybe V once, and that's it. But it has to be calculated for every single resample, just like you would calculate T star for every single resample. Well, suppose you didn't want to do asymptotics. What else could you do? Well, there's something called, well, shoot. I am going out of order here. I need to talk about something here first. So this asymptotic variance for T. How is this going to come about? Well, hopefully in 883, all we talked about a delta method. Does that sound familiar? In 883. 980, yes. Right? Okay. You should all be shaking your heads yes in the front row. No? I got a mixture of responses. But in 883 now, do you talk about the delta method? Okay. If you didn't, it's in Cassellenberger's book. It's just I know, like when I took a course like 883, we did not talk about the delta method. I really wish my professor would have, because it would have made my life easier later on when professors assumed I knew what the delta method was. But you at least briefly talk about the delta method. I will do a review of the delta method when we get to section, the second part of the chapter 2 notes. And in that case, you're doing what's called the parametric delta method. But there's also something called the non-parametric delta method that doesn't do any of this distribution stuff. And we're going to spend a lot of time on that in section 2.7. And that's what's going to allow us to get a thing to put in there for V and V star. Or let's say a different alternative than that. So let's take a look at an example. This goes back to the air conditioning data. Again, what we want to do here is we want to estimate the mean number of hours that the air conditioners will last on airplanes. And the original parametric setting that we looked at, if you remember, said let's let y be distributed exponential mu. So that meant T, our statistic of interest that estimates mu, happens to be a gamma n mu. The variance of T using the parametric assumptions is mu squared divided by n, which can be estimated, of course, by y bar squared divided by n. Okay, now before we talk about a bootstrap version of how to get a confidence interval for mu, let's talk about how to form an exact interval here. Now let me make sure that you understand what I mean by an exact interval, because this is a term that can often be misunderstood. Exact intervals in statistics do not mean that if you state 95% confidence that you truly have 95% confidence. It does not mean that. Rather, it means that you are using the exact probability distribution for the statistic of interest. So, for example, for those of you who took my Study 75 class, we talked about the Clapper-Pearson interval. That was an exact interval for a population proportion because we use a binomial distribution and its relationship with the beta distribution. Okay. So we can actually derive an exact interval for mu in this particular setting. Now, here, let's look at what z would be. Z is t minus theta divided by v to the 1/2 power. T is y bar, v is y bar squared divided by n for our setting here. And you do a little math, you come up with this quantity here. The key part is this mu divided by y bar. Well, y bar divided by mu itself, one could show using 882 stuff. Set 882 stuff is a gamma n1. Notice there's no other random variables in that quantity, and thus we have the distribution for z. Some variant of this gamma. Note also this means that z is a pivotal statistic. There's nothing unknown in there. Nothing unknown with respect to the distribution. Pivotal statistic. So, given that then, what I could do, I go one of two different ways. Here's the simpler way first. If I want to find a 1 minus alpha times 1 minus 2 times alpha times 100% confidence interval for mu. I simply work with our statistic, y bar divided by mu. I find a lower quantile from the distribution of gamma n1, find an upper quantile, do some algebra, so I just have mu in the middle, and this stuff right in here, then if you think of in terms of the observed values of the random variable, is our exact interval. So just emphasize this K inverse 1 minus alpha, so 1 minus alpha quantile from a gamma n1. Alternatively, what you could have done, even though it's not necessary, I do this for emphasis that, notice I'm not actually using Z itself in here. I'm using just part of Z. But if you did actually use Z itself, you could go through the exact same type of derivations. So for example, the distribution of Z then is the distribution of square root of n, 1 minus 1 over k, where k is a gamma and one random variable. Then put Z in the middle, put the quantiles now on the two sides, go through the algebra, and you get exactly the same interval. So that's our exact interval. We would expect that to be relatively good, since this is an exact interval. Well, what would we do for the parametric bootstrap? Well, now Z becomes Z star. We replace mu with the observed y bar. We replace the y bar with a y bar star. Okay. Now this y bar star divided by y bar, guess what? It also has a gamma n1 distribution. You know, we've already talked about the distribution of y bar star before. When we divide by y bar, what was y bar before in this gamma distribution now becomes 1. So then, what we end up with, since this is exactly the same, get the same interval for using the parametric bootstrap. One could just simply appeal to exactly what I did up here, except for now I put this in there instead. Of course, you get the same thing. Or instead, what one could do is actually start from the point of view of what Z star is, just like how I did with starting with what Z was, and you end up going through derivations to get exactly the same interval. So, I think this then leads to an important point then. Notice we had a pivotal statistic. When we started working then, and we derived the exact interval, then when we did the bootstrap with a pivotal statistic, look what we got. The exact interval again. The exact same one. That's one reason why we want to work with pivotal statistics. Okay. So, let's go through some of these computations so we can actually calculate the interval. Make sure I'm not getting ahead of myself here. So here's my interval that I presented to you before. Now, since I know the exact distribution of Z star, I could rewrite this instead as Z star with the subscript 1 minus alpha to represent with 1 minus alpha quantile from this exact distribution. And I could write this as Z star alpha. How do I find those quantities? Well, Z star 0.025 quantile would be the square root of n times the quantity 1 minus 1 over the 0.025 quantile from a gamma. So you could use the cube gamma function to find that, 0.5167. So here is my quantile from the distribution Z star. I could do the same thing to find the 0.975 quantile as well. So then once I have that, I can simply find my interval limits. T minus T star 1 minus alpha times the square root of y bar squared divided by n. So lower bound is 65.89, upper bound is 209.17. Here's just some of the R code that I would use to actually, let's say, calculate this in R quickly in terms of just plugging in the corresponding formulas into R syntax. Now, how would we do this if we actually wanted to take resamples? Of course, in this case, you wouldn't, because you know what the exact quantiles are. But again, just as a reminder, one would take R resamples from an exponential y bar. For every single resample, you're going to calculate T star, or in other words, y bar star, and also Z star, which would be y bar star minus y bar over the square root of y bar star squared divided by n. Calculate that Z star for every single resample. Find the R plus 1 times 1 minus alpha ordered value. Find the R plus 1 times alpha ordered value. And there's your Z stars. Even though someone wouldn't do this and actually do this, it's useful to actually do this on your own just to verify that you can do it. And the fact that since you know what the correct answer is, so we know what the distribution of Z star is, the stuff that you get from the Bootstrap here using the actual resample should match. It would be very, very close. Are there any questions? Now, I think sometimes when you, in this kind of an example, it's helpful. It might be difficult to first see all the derivations of everything that I did there. And it just might be one of those cases where you need to sit down after class, look through it on your own, make sure that you understand the derivations that you did. Okay, well, what would happen with the basic Bootstrap Confidence interval? Well, here's the formula, as we've seen before. Now, this is the formula that we would use with actual resamples. But in this particular case, we know the exact distribution of T star. Y bar star is distributed gamma n y bar. We've seen this before in previous problems. It's related to what we were doing for y bar divided by mu. So what that means then is that we can simply replace these T stars with actual quantiles from our gamma distribution. So how about I just call these quantiles y bar star, and then the subscript I have 1 minus alpha, for the 1 minus alpha quantile from that particular distribution, that statistic. Also do the same thing for y bar star alpha. So that's going to go in here, and that's going to go in there. Then I can go to the Q gamma function in R to find the corresponding quantiles. So quantile, the upper quantile is 177.28. The lower quantile is 55.85. You go through all the math, get 38.89 to 160.32 as the actual interval. Is this interval similar to the one that we just calculated? The previous interval was 65.89 to 209.1. No, it's not. What you're going to find out, as I guess mentioned towards the beginning here, this basic bootstrap interval, while it's very, very intuitive, it's not necessarily always the best. I will tell you now that it works best when you have a symmetric distribution. In Chapter 5, we'll see why that occurs. With a studentized bootstrap interval, it's typically a better interval to use. So I trust that result more than I do with the basic. Here's the usual t-distribution based confidence interval, because we do have a confidence interval for mu that we're finding here. So we could, if you really wanted to, even though your sample size is small, you could find the regular old confidence interval for mu, 21.52 to 194.6. This is, I think, closer to the exact interval that we had, or in other words, also the studentized bootstrap confidence interval that we had. But still, there are some differences. In particular, the lower bound. But remember, too, that this starts off assuming that y has a normal distribution in terms of its deprivation. Okay. So that takes us then to page 66. Let's talk about how we can do this interval with non-parametric bootstrap. So I'm going to use the boot function here. If you remember from when we used the boot function in the past, we need to create a function that calculates my statistic of interest. Now in this case, I'm going to actually need to calculate two different statistics in this function. The mean, and now also the variance. So I write calc.t gets a function. I'm going to pass in 2 bits of information, data and I. So first argument, the first line of code, d gets data I. This is going to allow me, when I contains the indices, so this allows me to get the resamples, find the sample size. The fourth line calculates the actual statistic that estimates my parameter, mu, so it calculates t. Here's my v. Okay, if it's based upon the original data, this would be v. If it's based upon a resample, this would be v star. I call this v.l, and you'll see why in section 2.7, because this ends up being actually the non-parametric delta method variance as well, that I'm going to show you. And that non-parametric delta method variance, actually it's a linear approximation to a statistic, so that's where the L comes from. Anyway. So I basically need a variance. Now, look at the variance that I'm using here. Come back here to work. I am simply using this, which is the usual, let's say, biased estimate of a variance for me. So normally we would use, if I wanted to estimate I want to estimate the variance of y bar. Of course, we would use s squared divided by n. If I use then the bias estimate of the variance, then that's why you have that 1 over n times n minus 1 over n times s squared. Now, why am I using that? Well, if you remember back towards the beginning of the non-parametric bootstrap section, we calculated the var star of y bar star. You could actually calculate that exactly, and that ends up being this. That's why I'm using that for my estimate of the variance. And because the non-parametric delta method ends up using this as an estimate of the variance as well. Now, in this kind of a setting, there is also some justification where you could just simply use s squared divided by n itself. Okay? I mean, if you know that there's going to be a better estimate out there, an unbiased estimate, there's nothing wrong with it. I'm trying to replicate some of the stuff that they do in the book too, so that's why I ended up using this one. Okay? Now at the very end here, I passed back two sets of information, my statistic and my variance, both. I'm going to need them when I do a studentized Bootstrap confidence interval. So when I run the function just with the original data itself, just to test it out, it's always good to do this. I highly recommend doing this. I get my usual sample mean that we've seen before, 108, and then my estimate of the variance is 1417.71. That's V. So to do the resample, I set a seed so I can reproduce my results. Use the boot function. Data is in Y. The statistic of interest is in calc.t. Just to reproduce the book, I'm using a small number of resamples here, 999. Otherwise, I would normally use more. Semi-equal ordinary to say I want a non-parametric bootstrap. Let me do this so you can see what happens. When I type boot.res here, what's new to us is the fact that now I have a second line of output here, because this corresponds to the variance. So this is V again, is what we saw before. Also, let's talk about what's inside of boot.res. So if I did boot.res $T0, notice how I get, again, the original stuff. But now I get two elements versus we were just getting one before when we only had one value given back to us. If I did head boot.res $T, look what I get. Now I get a 999 by 2 matrix of T stars and V stars. Here are the T stars, here are the V stars. So as I show in the notes, if I wanted to calculate, I guess I didn't do that. If I wanted to calculate Z1 star, it would be 169.16 minus 108.08 divided by the square root of 2207.19. That would be Z star 1. Now hopefully you remember that plot function, use it with objects that have a class of boot. When I say plot boot.res, look what's plotted. This is actually my T star distribution, and this is a QQ plot for T star itself. This occurs by default. The plot.boot function looks to the first indice in boot.res $T. If you want this set of plots for the V part, the V star part, well then there is an option or argument that you can put in there. Say plot boot.res comma index equal 2. If for some reason you want it. So, how about we find some quantiles now? In my basic Bootstrap confidence interval, I'm going to need quantiles from the distribution of T star. So I use the quantile function what we've done before. And let's say I want a 95% interval, so I'm going to need to take the 0.025, 0.975 quantile. And as a reminder here, I believe we talked about this before, I say type equal 1, so I get the quantile calculation to match what the book defines as a quantile. So I get 45.83 and 193. So the 193 will be T star 999 plus 1 times 0.0 times 0.975, which will be T star 975th order value. That's what 193 is. And I just kind of demonstrate that, showing you how you could do this without the quantile function as well. So if I wanted now a quantile from the distribution of, if I wanted this, G inverse 1 minus alpha given F hat, which can be equivalently expressed as G hat 1 minus alpha. In the book's notation, all I need to do is take my corresponding T star. In this case, this is going to be the 25th ordered one, and subtract off T for the 0.025 quantile. If you wanted to do that. Alternatively, just simply use the formula. So, for example, here's the upper bound. I take 2 times T minus T star, 975th ordered one, and I get 170.33. Lower bound is 23.167. Be careful here. It says it's a 97.5% interval. The reason why it says that is because, does anyone know why it says that? This is a 95% interval. A little bit there. Where this, and perhaps I needed to actually execute the code so you can see it better. Notice if I execute this segment of code, which allows me to find these T star quantiles, notice how you see a number there, 97.5%. Then when I form a data frame, first argument, I say name equal basic. That's just a label for you. Here's the lower bound. Here's the upper bound. And look what happens. See a 97.5% there? What R does, it carries over this label. We don't want it to, but it does. Does anyone know how this could be fixed? There's a variety of ways. Remember the as.numeric function? And so you see that label disappear. You see a 1 out here just because this was the first row. I think there's also, let's see, I believe there's another way to do this. Let's figure it out real fast. Let's see. Row.names equal null. Yep. So that's another one. I just wanted to point this out. It's a small, minor thing, but I don't want you to get confused thinking, oh, this is a 97.5% interval. No, it's not. But what about then the studentized interval? Well, here is how we find Z star. Simply take the first column from boot.res $t, subtract off the observed value t, which was calculated a long time ago in the program, and then divide by the square root of those V stars. So if I do that, here's my Z stars. You can find the quantiles using the quantile function, and then simply program in the corresponding formula into R to find the interval. 42.14 and 312.1.
If we hadn't calculated our T earlier, like you have it there in your Z star formula, you could pull it out of your boot.res as
You
well,
could.
right?
You could. Yes.
It would just be T0, right?
That's right. That's right. Yep. You could definitely.
The first one, T0, obviously.
Yeah.
Okay.
Yep. And that's sometimes easier to do. Now to emphasize how I did this calculation here, so this is where small little things here can cause you time in terms of trying to figure out what's going on here. Why doesn't my answer match up? So let me put in here the formula. Again, I'm trying to duplicate some stuff in the book. And so if you don't like what I did here, blame it on the book. Because this can be confusing. I speak from experience as a student who tried to use this book. This is the formula that was used. So notice here what's being used for V. It's the unbiased estimator. Again, in practice, I would typically use the unbiased estimator because it's unbiased. Why did I use the bias estimator previously? Well, again, I was trying to reproduce some stuff in the book, and that's why I used it in that calc.t function. So this is where it gets confusing. In Z Star itself, notice we are using the bias estimate of the variance. But in the interval itself, when you have a variance, when you have the V, the unbiased version is used. Sorry, that's just the way it is. But this also then leads into some good discussions of understanding exactly what the software package is doing, as you will shortly find out. Before I do that, I do want to mention, though, is that look how wide that interval is compared to the basic interval, which was 23 to 170. This interval is 42 to 312. What the main downfall of the studentized bootstrap interval is it can be wide. And without getting all the reasons right now, the reason why that occurs is because look at the denominator of Z star. If you have some small variances, what's going to happen to the distribution of Z star? It's going to get wide. It's going to be very wide. That's why that happens. And so the main downfall of using this particular kind of interval is that you often will get a wide interval. Okay. Now there's actually an easier way to do some of these calculations. Why do we do it the hard way first? Well, it's because we need to know what the software package is doing. So there's a function R called boot.ci. Isn't that nice? If I say for the first argument, boot.out is equal to boot.res, confidence level 95%, type equal, put in your intervals that you want, basic, that stud there is studentized, and then there's another kind of interval that we'll look at really shortly called normal. You'll see what it is later. And here are the intervals. 23.2 to 170.3, which matches what we had with the basic. Studentized 45 to 303.4. It doesn't match. Okay. So I missed this when I took the course as a student, that this didn't match. Then when I was first teaching it, I was like, wait a second, what's going on here? And so many hours later, I figured it out. Here's what's happening. And it just has to do with what's being used for variance. Okay? If, excuse me, the way, notice we're not saying anything about the exact form of Z star here. How does R know then what to use for Z star? Well, what it does, it looks. Let me use, I guess you could say this is pseudocode. When it calculates Z itself, it would calculate it this way, or let's do Z Star. It would calculate it this way: boot.res $t bracket comma 1, as you would expect, minus boot, this corresponds to what was asked earlier, boot.res $t0 bracket 1 in bracket. So this is T divided by then boot.res $t bracket comma 2. All this to the 1/2 power. So it automatically looks always to the first column for T. It automatically always looks to the second column for the variance. Even if you had, let's say, a calc.t that for some reason calculated 3 different things, it always looks to the first and the second column. There are ways, look at the help for boot.ci. There are ways to change that. There are arguments that you can give. Now, when the interval is actually being calculated then, so you have t minus z star, I'll just do the lower bound here, 1 minus alpha. In order to calculate then this variance, it actually goes to what's in T0. That's why this interval is different from the one I calculated. Because remember what I did here? I instead used the unbiased estimator. It's using the bias estimator that came from the statistic itself. So it's a minor thing, but it can take a long time if you're not fully understanding what's being calculated. It can take you some time really to figure out why are things different. If you wanted to specify the actual variance to use, like the variance that I use when I was calculating the interval myself without boot.ci, there's an argument called var.t0, and you can specify whatever the variance would be. And now my answer matches. Or the answer from boot.ci matches what I had before. Okay. We are just about out of time here. I think you have enough background now to do the confidence interval part of the project, but since there's still a little bit more that I want to talk about in this chapter, why don't we just move back the due date for the project to, well, let's say noon on Friday. Okay, so that you have Thursday's class to ask me questions, so have them. And also maybe some of the stuff that we talk about on Thursday in class might help out. I don't think it's going to make much of a difference, but since we're not done with the confidence interval section yet, I don't mind moving back the due date for the project to Friday. Friday at noon. Are there any questions about that? Okay, that's it for today.